Hey everyone, my name is Sam, and I'm a second year PhD student at Harvard University. Today, I'll be telling you a little bit about an emerging workload in the recommendation space, why we, systems researchers, should care about it, and potential steps that we can take to address this problem. So, for those of you who aren't familiar with recommendation, what a recommendation system does is that it takes in you and your item preferences and generates relevant recommendations. And the reason why we, systems researchers, have started to care more about this problem is that it's an extremely important workload in real data centers. For example, when we take a closer look at Facebook's data centers, we see that over 80% of their AI inference cycles are spent on recommendation related tasks. And over the past year or so, there have been more than a couple of proposed system solutions. And if we take a closer look at these DNN-based recommender systems, we'll see a common trend among the current system solutions. They either optimize the embedding table accesses with caching or NDP solutions, or tackle the DNN stacks with systolic array style accelerators. However, what I want to talk about today is how graph neural networks, one of the hottest research topics in the ML community, are about to play a big role in this discussion. So if we take a look at a GNN for recommendation, we see that they operate on graph-based data. By not treating each user and item as independent entities, we learn their relationships, leading to even better recommendation accuracy. With this increased accuracy, however, comes a new set of compute challenges, namely graph traversal and processing and GNN model-specific compute. And keep in mind, this is all in conjunction with the embedding access and DNN problems that we've been dealing with for deep recommender systems. So this leads us to a question of how should we reason about these compute challenges? And that's what I've been working on lately, taking state-of-the-art GNN recommender systems like this one shown in the figure and characterizing their bottlenecks. For example, what we've seen so far is that first, the traditional DNN stacks shown in black pale in comparison to GNN compute shown in red and blue. And second, attention mechanism shown in yellow is an integral component to GNNs for recommendation. And this attention mechanism is quite unique in that it's not present in traditional GNN workloads, but only for GNN recommendation workloads. That's just a preview of some of the work that we've been doing. In general, we want to identify these specific compute bottlenecks first, and then start thinking about system solutions to handle them. Thanks for listening.